All right, so part three of our admittedly a little bit cumbersome discussion of limits. So far, we've talked about what limits are. We've talked about continuity. We've talked about what asymptotes are, our new way of defining an asymptote now based on a limit instead of just looking at the graph. Well, now we're going to talk about what we can do with these limits. So we're going to start with just some properties of limits. And for this section, just for some shorthand, I'm going to use A to represent the limit as x approaches c of f of x, and then b to represent the limit of as x approaches c of g of x. So a is for the limit of f, b is for the limit of g, just to save myself some time. A lot of these are fairly intuitive, believe it or not. So if I have the limit of a sum of functions or a difference of functions, as you see in number 1, right, the limit as x approaches c of f plus g, well, the limit of the sum is the same as just the sum of the limits. So the limit of f plus g is just the limit of f plus or minus, depending on if I'm adding or subtracting, the limit of g. And this is helpful to us, this is important to us, because this means I can take any function and I can split my function up in two pieces by term, which is really useful for us when we're actually calculating a limit, especially algebraically. The same logic applies with the product and quotient, right? The limit of a product is the product of the limits, and the limit of a quotient is the quotient of the limits. Of course, this comes with the catch that the limit of g cannot be 0. These are pretty intuitive. This sort of thought process and this sort of logic is going to come back in a couple sections when we talk about derivatives and a whole bunch of different properties of derivatives. But for now, whatever the operation is between the functions, we can also do that operation between the limits. Here, number 4, right, if I have a constant times a function, I can actually ignore the constant for the time being and consider just the limit of the function. I can kind of pull that constant out front. So this would be like saying k times a. And then likewise with a power. So I'm going to write it this way, kind of longhand first. So the limit of a function being raised to the power is the same as the limit of the function being raised to the power. The difference is in the way I worded it, right? The limit of a function being raised to a power versus the limit of a function being raised to a power. Of course, my power needs to be some kind of a rational number, which in this case we're also including whole numbers here, I suppose. And of course I also need my number to that power to exist. Right? I can't have anything here like -1 to the 1/2, right? Because that obviously does not exist. So that's what I'm looking at with my properties here. Maybe I'll type it up, give you guys a PDF you can have at your disposal for reference. But here's what we're dealing with our properties of limits. So we're going to use these. We're going to actually apply these now. Find the limit as x approaches infinity of x plus 1 over 2x plus 3. This, by the way, is just a fancy way of also asking you to find the horizontal asymptote. If you remember from our discussion in part 2. The horizontal asymptote is the value that the function approaches as x approaches either plus or minus infinity, and that's exactly what we're looking at here. One big tip, well, two big tips, I guess. One is prior knowledge, so this is some kind of information that you may be expected to know at this point, and that would be to say that the limit as x approaches infinity of 1 over x is 0, right? And we can conceptualize this relatively easily. Right, if I plug in a bigger number and a bigger number and a bigger number into this function, right, if I were to plug in, say like 1, 10, 100, 1000, right? I'm going to get 1.1, 0.01, 0.001. You can see that my number gets closer and closer and closer to 0 without actually getting to 0, hence my limit of the reciprocal function being 0. The other major tip that will be helpful is this. When you're finding the limit of a rational function, finding the limit of a rational function. One thing I can do to make this easier is to divide the numerator and denominator by the highest power of x. So divide the numerator and the denominator by the highest power of x. I'll explain what that means in a minute once we start working on this problem. Let me just paste this down here. Okay, so how do I start working with this? Well, I can use my prior knowledge and I can use my tip here. So right now there's not a whole lot I can do because if I were just to go ahead and consider increasingly larger values of x, both of these sides would approach infinity. Both the numerator and denominator would approach infinity. The first thing I want to do is apply that quotient property that I have. Right? I want to look at what happens when I take the limit of x plus 1 and then take the limit of 2x plus 3. Because as we said, the limit of a quotient and the quotient of the limits are the same, so I can look at my function this way. Now, if I were just to go ahead and evaluate this as is, as I said, we wind up getting this to approach infinity on the top, because this number is just going to get bigger and bigger. And same thing with the denominator as well. So we need to find some way to reduce or simplify this function or change this function in order to actually make it work out for us, in order to actually calculate its limit. So the way we're going to do that is to apply our rule here, to apply our tip. So we're going to divide the numerator and denominator both by the highest power of x. And for the numerator, that is just x. And for the denominator, that's also just x. So if I divide all of my terms by x in the numerator, I get 1 plus 1 over x. And if I divide my denominator by its highest power of x, I'm going to get 2 plus 3 over x. And now what's great about this is I can actually calculate a limit. The limit of a sum is the sum of the limits, right? So I'm just going to take this term by term. Well, the limit of 1 is just 1. Right? Nothing here is going to matter. Nothing here is going to change. The limit of 1 is just 1. Right? No matter what happens to x, the value is always 1. And we just said that the limit as x approaches infinity of 1 over x, we said is equal to 0. So in my numerator, I'm left with just 1. 1 plus 0 is 1. In my denominator, the limit of a constant, again, is just that number, so the limit of 2 is just 2. And then the same idea over here, 3 over x. As I plug in increasingly larger numbers for x, my number is going to get smaller and smaller. I'll have 0.3, 0.03, 0.003, and so on. So we can also say that in my denominator, this right here is going to approach 0. So 2 plus 0 is 2, so denominator is 2, and the limit of my function is 1/2. If you're wondering how I got to this point, remember I said when we started the problem that a problem like this where I'm dealing with an infinite limit of a rational function, it's the same as finding the horizontal asymptote of f of x. Well, if you think back to our horizontal asymptote rules, if I want to almost check this function, If I think back to my horizontal asymptote rules, the degree of the numerator and the degree of the denominator are equal. They're both 1, which means that there is a horizontal asymptote equal to the ratio of the leading coefficients. Well, the leading coefficient in the numerator is 1, and the leading coefficient in the denominator is 2. So sure enough, using our rules that we've learned before, we show that this works out. We can check that this works out. I could also graph it if I wanted to, but I'm not gonna right now. And we would see graphically that there's a horizontal asymptote at 1/2 as well. This trick where we're really kind of breaking down math here, it feels a little bit, it feels wrong, right? To just start working inside the fraction, splitting things up, calling things 0 for whatever reason we feel like. It all seems very, very arbitrary. I promise you it is not. And I promise you that this is a really important skill for the basis of calculus, and a lot of it will help us set up the explanations of some of our bigger topics in calculus. Differentials, derivatives, the different rules we have for derivatives, integration even in Calc 2, all of that. But for now, we're going to move on, and we're going to talk about the limits of sequences. So in Chapter 1, I'll keep the same color. In Chapter 1, we had talked about sequences. And we remember that my curly bracket notation is my way of notating a sequence with my a sub n. Remember that IB will use a U instead of an A. It's, for me, just personal preference. So we can actually find the limit of a sequence, right? A lot of times when we talk about sequences, we can look at it in terms of some kind of a function, right? Our general term gives me a rule, no different than a function does. Well, fortunately for a limit of a sequence, that's exactly how I'm going to look at this. We're just going to treat the sequence as a function. So we're going to change our definition now to say this. If the limit as n approaches infinity, so I go out infinitely many terms in my sequence, is equal to some number L. And of course that has to be a real number L. Here we're just kind of being formal. Then the sequence converges. We've talked about convergence a little bit in Chapter 1. Right, we hinted at it a little bit in Chapter 1. Now we're really going to talk about it in depth. And of course, if the sequence does not converge, then it diverges. So as long as the limit exists of my function, as long as the limit exists of my sequence, rather, then my sequence converges to that number. So let's look at this first. Determine if each sequence, should be singular sequence, converges or diverges, and if the sequence converges, give the limit. Here we're just going to kind of look at it. We just want to see, is this sequence going anywhere? Is it approaching a specific number, or is it just going on forever? Well, here, 1, -1, 1, -1, 1, and we can assume that this just continues, -1, 1, -1, 1. This is just going back and forth between 1 and -1. This isn't going anywhere, so this diverges, right? It's not approaching a specific number. Likewise with B, 2, 4, 6, 8, we can assume that this continues 10, 12, 14, 16, 18. This is just getting larger and larger, approaching infinity. Because we're dealing with a sequence, however, we're not going to say that the limit exists. We're going to say that this diverges. It does not approach a number. So this is where it's a little bit different than just a function. I'm not approaching a real number, so I'm going to say that my sequence diverges, just like we said it did in Chapter 1. On part C, this is actually kind of what we've talked about just now in the last example, right? This would be 0.1, 0.01, 0.001. Okay. Am I approaching a number? This time I am. My terms are getting smaller and smaller. They're getting closer and closer to 0. So we're going to say this converges because we got it to approach a number. So the limit of my sequence is 0. Likewise with part D, I'm getting closer and closer and closer to 2.4 without actually getting there. And so we say the sequence converges to 2.4. So here's my example algebraically. If I want to find the limit as n approaches infinity, so as I go out n terms, infinitely many terms, of this rational expression here. Well, I'm going to start by employing the same trick I did before. We're going to use our division trick. So we know a couple things. We first know that the limit of a quotient is equal to the quotient of the limits, so I can actually kind of break this up. And now I can use my division trick, because right now, if I were to just plug in increasingly larger terms forever and ever and ever, both of my functions would approach infinity. Right? Both my numerator and my denominator would approach infinity. So I need to simplify this. I need to change something about this, and this is where the division trick comes into play. Divide by the highest power of n on both numerator and denominator. So for the numerator, that's n cubed. So I'll get 1 plus 4 over n squared. Same idea here, n cubed. So I have 2 over 1 minus n cubed. And we want to look at this piece by piece. Obviously, the limit of a constant is just that constant, so that stays, that 1 stays. And then as I plug in larger and larger n values, this whole thing is going to approach 0, so we say the limit is 0. Right? Any of these simpler rational functions, the limit tends to approach 0. So likewise in the denominator, limit of a constant is a constant, so that stays 2. The bigger values I plug in for n, the closer I get to 0 in this case. So if I were to simplify this all together, I get 1/2. And again, I could graph this if I want. I could use my horizontal asymptote rules if I want to confirm that this is true. So one last example, and this is to say that for an infinite geometric series, this is something we've already talked about, right? We talked about this in 1.2. For an infinite geometric series, when the common ratio is between -1 and 1, or we say the absolute value of the common ratio is less than 1, then the series converges to the sum given by the formula here. Right, we've seen this before, we've dealt with this before. It is on our formula booklet, which is great. So let's figure out if this series converges. 2 to the n plus 3 to the n over 5 to the n. First thought might be how. Let's take it, break it apart, deal with it piece by piece. We know this series converges if the limit exists. Well, sums and limits are closely related. So the first thing I'm going to do to simplify this a little bit is to split this up and divide through. So I can actually take my 2 to the n plus 3 to the n over 5 to the n and split it up as 2 to the n over 5 to the n plus 3 to the n over 5 to the n. And I know I'm going to know this converges if the limits exist for both of these. So I actually, instead of considering the sum right now, I'm going to consider the limit. Okay. Well, of course, the sum of a limit, or sorry, the limit of a sum is the same as the sum of a limit, so I can actually kind of split this up and look at this piece by piece, which for this example is extremely helpful. And let's take this one at a time. So for my first limit, I'm actually going to maybe break this up. So look at this in separate pieces to start. So for my first limit, the first thing I can maybe do to manipulate this is to say that this is just 2/5 to the n, which is a geometric series, right? Its first term is 1. Its common ratio is 2/5, which means this is going to converge, and it's going to converge to a term, or to a number which is equal to the sum of the series. So this is going to be 1/3/5, which is 5/3. We're going to follow the same exact process with my second limit here. So the limit of 3 to the n over 5 to the n. If you want to try this for yourself, you're more than welcome to pause the video and test it out, make sure you understand it. Will be the limit as n approaches infinity of, using my properties of exponents, 3/5 to the n. So I'm going to get 1, the first term is 1, over 1 minus 3/5, 1 over 2/5, which is 5/2. So putting this back together, the limit of, in red, we said was 5/3, and the limit in green we said was 5/2. So if I add these together, I need to make a common denominator first. All right, so I'm going to get 10/6 and 15/6. So I get 25/6. So my limit does exist. This does converge. And it converges to 25/6. So this problem can be a little bit complicated and a little bit scary looking to start. You might have noticed by now that if you take it and break it down, as we've done, right? We've played with it, we've split it into smaller bite-sized pieces, and we're able to take this step by step, look at it in a way that we can apply what we've already learned instead of just looking at the big picture and getting overwhelmed. So taking this chunk by chunk, bit by bit, and we work it down to actually prove that the sequence does in fact converge.